Hello everyone, my name is Gustavo. I'm staff engineer at SLAC National Accelerator Laboratory and a PhD candidate at Stanford University. And I'll be talking about our project titled Case Study on Sustainable Farm Electricity Management. This project is funded by ARPA under the NODES program. The outline of the talk will address the following topics. First, I'll introduce the overall concept of the project, which is called Powernet. Then I'll talk about the lab infrastructure we built to be able to simulate and experiment with real device before going to the field. Then I'll transition to the specific case study that is the focus of this talk. The whole idea of Powernet started from the simple observation that the grid is changing. As depicted in this slide, we're all aware of the increased penetration of renewable energy, solar and wind, for example, into the transmission distribution system. Moreover, the distribution system is seeing a large number of behind-the-meter resources, such as battery and storage systems, rooftop solar, smart loads and smart meters, and electric vehicles being added. Most of these resources have some form of communication to the external world via a cloud system. This communication capability enables a new way of controlling these resources and allow a high-level system to coordinate large numbers of these small resources from a distribution system perspective, so that it aggregates these resources and support grid operations while maximizing customer benefits. Powernet is an open source platform that bridges the gap between the distribution system and the behind-the-meter resources. The Powernet platform is broken down into two main components. At the top level, the cloud coordinator is responsible for coordinating and aggregating behind-the-meter resource. It optimizes the dispatch of those resources, accounting for the network constraints, electricity costs, and user preference. Additionally, it utilizes novel machine learning techniques to forecast future load demand and weather to ensure the system is able to respond to grid service such as ramping and regulation. The cloud coordinator calculates a power profile signal for the home hubs to follow and broadcast that information to all participating entities. In the lower layer, we have the home hub. The home hub provides the local intelligence for the home to control its resource. The home hub sends aggregate information to ensure privacy is maintained to the cloud coordinator based on its capabilities and receives a signal to follow when the system is participating in ancillary service or supporting grid operations in general. The home hub disaggregates the signal by performing optimization to maximize customer benefits while still ensuring the signals follow and send a command to each controllable resource. Additionally, the home hub forecasts future load consumption based on historical data and generate potential scenarios and quantify its average flexibility to respond to a signal. In order to test the proposed solution, we built a state-of-the-art lab at Stanford University where we were able to experiment. This lab features a regenerative grid emulator that feeds the experimental side of the lab and also is capable to implement voltage and frequency sags and swells. Additionally, behind-the-meter resources such as solar, battery, and storage systems, smart and regular loads are all connected to the same network. Each load and resource are individually measured and also the sub-circuit they are connected. Here we show the performance of our simulation where 10 lab homes with real loads and resources were connected to a simulator with around 13,000 homes. Here we show the system following a regulation signal. On the left, we show the aggregation of homes from the simulation and the lab following the signal. The blue curve shows the tracking signal and the orange shows the system performance. On the right, we show a subset of homes being controlled by individual home hubs following the signal each of them have received from the cloud coordinator. From the initial concept developed, we realized that this solution is not only applicable for the residential and commercial sectors only, but in pretty much any sector that utilize electricity and are leveraging behind the meter resource. One sector that is highly overlooked but heavily depends on electricity is the agriculture sector. Diving deep into this sector, the left graph shows electricity is the third highest form of energy consumption. Looking closer to different ag business, the livestock sector has electricity expenses as a large percentage of the overall expense compared to other segments, which is depicted in the middle graph. Finally, with the livestock, dairy, and poultry are the ones where electricity expenses are more significant. For this study, we look specifically into dairy. From a market perspective, in the dairy industry alone, there are around 43,000 licensed dairies in the US, milking 9.3 million cows approximately. This figure shows the top 10 states in the US by number of cows for the last 4 years. Although the number of dairies is decreasing to the consolidation process, the number of cows is very stable, which means that farms are getting bigger every year. That simply means that farm operators are managing more load devices, which means more total electric power consumption. From a usage standpoint, the breakdown depends on the size of the farm, herd size, and other factors, but milk cooling and ventilation numbers do not vary much by farm. Milk cooling operates 24/7, all year long. However, they are not easily accessible to implement solutions to offset energy utilization from grid without impacting operations, and equipment reliability is detrimental. Downtime in operation can hurt the entire business. Ventilation, on the other hand, is seasonal and operates roughly 12 to 18 hours a day. Equipment are easily accessible and easy to control. Also, reliability is important, but the time scale is longer. Finally, ventilation load is the main cause of load peaks, which ultimately affects electricity consumption. Why ventilation is important? Cows not like heat, and the impact of heat can create multiple problems that ultimately affect milk production and health of animals. A common metric used by dairy farmers to manage heat stress is the temperature and index humidity. Temperature and humidity index. If THI is above 72, it is assumed that cows are experiencing heat stress. As ventilation is required mainly during the day, having an understanding of the rate structure is key to develop strategies to help reduce electricity consumption. Here we represent the current rate structure the dairy farm faces. The key takeaways are, number one, summer and winter have different rate structures where costs in summer are higher and it has peak hours from noon to 6 and off-peak hours, all other hours. Winter, on the other hand, has partial peak and off-peak hours. Number two, summer has different energy costs for weekdays and weekends. And number three, the demand component of the rate structure is significantly higher during summer, and there are two types of demand charges in there that the dairy incurs. Maximum peak hours demand and maximum demand, whereas in the winter, there's only the maximum demand. And the costs are presented in this slide. From a cost perspective, we looked into the dairy farm electricity costs for each month from 2016 to beginning of 2018. The seasonality has a big impact in energy and demand consumption. On the left, we show the demand component, and there's a clear seasonality pattern for summer, which spans from May through October, and winter. Ventilation has the highest contribution in demand. On the right, we show the electricity costs. Once again, we can see the costs are a lot higher in the summer compared to the winter. One clarification, for the year of 2017, the farm installed a 2.2 megawatt solar system to offset the energy costs under the net and energy metering aggregation program. In the early 2018, though, one can see the cost during summer spiked again as more freestall barns were added to this specific dairy farm, and NEMA does not apply to demand, but only to energy and up to a maximum amount. The next step based on the rate structure was to break down system operations. In this farm, fans are 1 horsepower nameplate capacity. Also, as they are induction machines, they tend to have high inrush currents and low power factor. These two characteristics can negatively affect the power system. We then look at the power profile of fans in half of the barn as they are in their own electrical circuit and identify its typical usage during the summer. Fans turn on when temperature goes above a preset threshold. In this specific case, 72 Fahrenheit, and turns off when temperature goes below this threshold. In a typical summer day, fans are usually on starting around 8 a.m. and turn off around 10 p.m. Therefore, they are utilizing power during the entire peak hour. Then we analyze the potential contribution of solar and its effects in the fan load profile. Solar has the potential to offset consumption for the majority of the day, including the peak hours, but can help much towards the end tail of the day. The battery contribution can help anytime during the day, whether through energy arbitrage or peak reduction in the last final hours. From this analysis, we chose the hardware that would be utilized. The solar system we used was developed by Suntech Drive and called Pico Blender. This is a smart solar powered variable frequency drive, or VFD, that is able to blend solar and grid power and grid to power the fan. The Pico Blender was installed in each fan with a solar capacity of approximately 1.6 kilowatt per fan. For the battery, we used two Sonnen units with a capacity of 16 kilowatt hours each for a total of 32 kilowatt hours. After the hardware selection, we designed and implemented the system in the field. The setup is depicted in this aerial picture of two adjacent barns in the dairy farm. The bottom barn is the one used for testing, where the north pen is used as the control and the south pen is used as the test. This picture also shows the solar panel, sensors, and control room installed to actively monitor relevant parameters of the system. Here we show the system installed in the field. In the left, we show inside the test pen, where the Pico Blender is installed by the fan. Look at the yellow box. In the middle, we show the two Sonnen units inside the control room, and on the right, we show the control room. On the software side, we developed the framework shown in the left. The data block is in charge of communication and storing the data. It leverages different application programming interfaces to send and receive information from devices. Optimization analytics is performed in the cloud by the cloud coordinator, and control actions are sent back to the power hub and then to the devices. Visualizations, statistics, and metrics are provided through the user interface, and in case of communication loss, a preset default operation takes place. On the right, we show the data block with all the data that Power Hub will be utilizing. It shows each source and whether it's one-way or two-way communication. This data is sent to the Power Hub cloud instance where it gets processed and routed to the specific application. Within the optimization and analytics block, load and solar forecasts are required to provide information to the optimization algorithms. Because historical data is utilized to generate models for both load and solar forecasts, these models become less accurate the further in the future we try to forecast. In order to minimize the impacts of these errors, a model predictive control optimization framework was utilized. The MPC formulation has the following characteristics. 1, it accounts for both demand charge and energy costs. 2, it utilizes a 15-minute time resolution as demand charges are calculated based on the average power during a 15-minute interval. It controls batteries and fans to achieve objectives. Number 4, the optimization horizon is 2 days. And lastly, the monthly demand charge is weighted by a discount factor to better account for how it is charged by the utility. Here we show the mathematical formulation of the optimizer. The objective function has 4 terms: an energy cost, a demand cost, a battery degradation, and the THI variation. The system constraints are battery power and energy, fan speed, and THI model based on fan speed. As the current setup does not monitor cow score body temperature, but only ambient conditions, it was decided not to use the THI model based on the fan speed in the current implementation. It will be added in the future work, and more explanation about why it will be presented in the analysis and results. In the next slide, we present the results by first showing the savings due to solar for each month from July to October of 2019, and then we present the results of the solar plus battery solution. In this slide, we show the July results. In the top right graph, we show for each day in July, the total power in blue, solar power contribution in green, and grid power in orange. Note that solar power and grid power are mislabeled here. Sorry about that. In the top right, we show 3 consecutive days. One can see that in the last day, the solar contribution is spiking as it was a cloudy day. Also, solar contribution helps offset a large portion of the consumption, but towards the end of the day, when the sun sets, the power has to come from the grid. In this sample, fans were on for around 15 hours, from 7 a.m. to 10 p.m. In the bottom graph, we show the solar and grid contribution to power fans in a bar plot. The red line shows how much in percentage the solar contributed to power the fans. For most days, solar contributed between 40 and 60%. In the bottom right, we show how much savings the proposed solution generated compared to the system without solar for the test pan, and the potential savings if the solution was implemented in a single barn, which has 2 pans, and for the entire farm, which has 10 barns. This accounts for over 47% in savings. Similar to the previous slide, here we show the savings for each of the following months. Note that there are a few days in October that fans were not even on because the temperature was below the threshold. The savings were 47.5% for August, 42% for September, and 31.2% for October. For the solar plus battery case, based on the data collected during the initial months of the experiment, we simulated the system performance when battery was added. In the left graph, we show 3 consecutive days in July. The blue curve shows the power that would be coming from the grid with solar only. The green curve shows the actual power that is being utilized by the grid after solar and battery contribution, and the orange shows the battery behavior. In this graph, the algorithm prioritized the demand charge component, and one can see the reduction in the peak towards the end of the day. The right graph shows a similar result, but the algorithm prioritizing energy arbitrage. One can see from the offset across the day between the solar-only solution, the blue curve, and green curve, which represents solar plus battery. Also, note the difference between the battery profiles in both graphs. After the simulation, the solar plus battery solution was implemented in the field to validate the simulation. This plot shows 1 day in October of the algorithm performance. We show 4 different curves. The blue curve shows what the control pen consumed during the same time of the experiment. Remember that the control pen is the standard setup in the farm without solar or batteries, just the fan load. The red curve called virtual fans is showing what the fans load would have consumed in the test pen without solar and battery, similar to the control pen. The green curve, which represents the test fans, shows the fans plus solar, and the orange curve shows the full solution, fans plus solar plus battery. Note that the orange curve follows closely the simulation results and clearly reduces the peak towards the end of the day, and thus contributing to the demand charge reduction. Here is a summary of the effects of the battery. On top of the solar presented in the previous slides, The left graph shows how much savings the battery could achieve from each of the components of the rate structure, energy in gray, peak demand charge in orange, and demand charge in blue. The table on the right shows the percentage savings after solar for each month. The key takeaways are: 1, battery savings has little monthly dependency since capacity is the limiting factor, and 2, arbitrage makes up the majority of savings under the current price tariff. The proposed solution not only supports the reduction of electricity costs, but has also other secondary benefits for the health of the system. In the left graph, we show the power factor of the control panel. When fans are on, the power factor becomes 0.65. This is expected as fans are inductive machines and they have this intrinsic characteristic of lower power factor. The low power factor puts a lot of strain to the system if not properly managed, and some utilities even charge a fee for a poor power factor, which is usually below 0.8. On the right, we show how the power factor looks like when solar is generating and when battery is discharging. Looking at the highlighted area shown in 1, we can see that the average power factor when solar is being generated is boosted from 0.65 to 0.87. This is because the VFD technology provides a power factor correction. In the highlighted area 2, we show another aspect of the system. When the batteries are discharging to support demand charges, it also provides grid support, more specifically voltage support by injecting reactive power in the system. This is a requirement by all inverters that puts power back to the grid to provide voltage support. One clarification: when load becomes close to zero, in other words, fans are turned off, batteries stop charging and discharge, the power factor becomes irrelevant as there is no power being drawn from the fans. Therefore, the abrupt spikes in the power factor curve for the test pan graph is due to the fans and batteries turning on and off. The last analysis performed was looking into the barn thermodynamics, which basically looks into the THI and fan model mentioned when we explained the optimization. From the measurements collected in the field, we looked into understanding how barns' internal temperature and humidity were affected by the airflow generated by the fans. The top left graph shows the daily profile of power. This graph was used to identify when the fans were turned on. Around 8:30 a.m., looking at the other graphs, one can see that there is no significant changes in patterns after fans were on for either temperature, humidity, or THI. Therefore, in order to create a representative model of the fans affected, of how the fans affect cows, core body temperature, ambient measurements are not good enough as they do not capture the evaporative cooling the animals are experiencing due to airflow. Thus, other sensors, such as thermal cameras, would have to be installed to capture the real core body temperature of cows that ultimately provides information about whether the animals are under heat stress or not. So in conclusion, to finalize the presentation, solar-only solution average savings during summer season was approximately around 42%. The solar plus battery solution average savings during the summer season was approximately 59%. And also THI alone is not indicator of cow's comfort, mainly because it does not capture effects of evaporative cooling. The future steps on this project is actually utilizing thermal imaging to passively measure cow's core body temperature. That will actually allow us closing the loop and control system to prevent heat stress while minimizing electricity consumption. Also evaluating potential of deployed technologies for the entire farm ecosystem, looking into milking facility, irrigation system, and also lighting. Finally, adding grid service support capabilities to farm resources, such as demand response, ramping, and regulation services. That's all my presentation. Let me know if you have any questions. Thanks.